Hello, today we will present about our group assignment for subject Mathematical Physics. Our assignment is to solve the differential equation question. I am Ayu Asmida and this is my group members Elijah Ling and Muhammad Daniel Izwan.
Now we are going to present about the coil-over oscillation. The coil-over oscillation on a bumpy road is modeled using a second-order ordinary differential equation in which the damping force is included because of the existence of the damper. The spring is assumed to be at its equilibrium length in the unperturbed state, and the vehicle weight is neglected. To analyze the coil-over oscillation, we have to use the second-order ordinary differential equation for damp oscillation shown in this line. In this equation, M is the mass of the load, C is the damping coefficient, K is the spring constant of coil-over, X is the displacement of oscillation, and T is the time taken. To derive the solutions for this second-order ordinary differential equation, first we have to understand that the square of the angular frequency of oscillation, which is given by omega square, is equals to spring constant K divided by mass of load M. And 2B is equals to damping coefficient C divided by mass of load M. Using these relations, we divide both sides of the equation by mass of load M to find this form of equation. Then we use this homogeneous equation to find its roots, which is given by negative b plus minus square root b square minus omega square. For under damped oscillation, in which b square is less than omega square, the roots will be complex roots, and the solution, which is the displacement of oscillation, will be both exponential and trigonometric. As a result, the solution will be in this form. For critically damped oscillation, in which b square is equals to omega square, the roots will be real and equal, which are both equals to negative b, and the solution, which is the displacement of oscillation, will be in this form. For overdamped oscillation, in which b square is more than omega square, the roots will be real and distinct, and the solution, which is the displacement of oscillation, will be in this form.
Next, we assume mass is 2.236 kg and spring constant 15.811 Newton per meter. There are 4 conditions: undamped, underdamped, overdamped, and critically damped. For the zero damping, our natural coefficient is set to 0.65 radians per second. Frequency this gives us a clear and omega value of 2.659 radians per second. Finally, we substitute this value into our main graph equation as radians per second. This displacement versus time graph illustrates an undamped system. Without any damping to dissipate energy, the system repeats periodically, oscillating continuously with a constant amplitude. Here, C is 6.082, resulting in complex root. This creates an underdamped system where the motion oscillates but exponentially decays over time. This graph illustrates underdamping. Here, the system oscillates back and forth, but notice how the amplitude gradually decreases over time until it finally comes to rest. With a high damping coefficient of 16.733, we get 2 real negative roots. The system heavily resists motion, decaying slowly without any oscillation. This displacement versus time graph illustrates overdamping. Because the damping force is so heavy, there is no oscillation, and the system returns to equilibrium much more slowly. At a critical damping value of 11.891, we get a repeated real root. This allows the system to return to equilibrium in the fastest time possible. This graph illustrates critical damping. Notice how the system returns to its equilibrium position in the shortest possible time without oscillating.
Discussion: undamped oscillation. Graph behavior. In the absence of damping, the coil-over has no spring in the system. The displacement versus time graph is a perfect sinusoidal wave with constant amplitude. Implication for automobiles: this is highly practical. Passenger will experience continuous vibration, and the vehicle is unstable at high speed. It highlighting why damping is essential in suspension system. Discussion under damped oscillation. Graph behavior. The displacement graph shows oscillation that decreases in amplitude. The system still oscillates, but each cycle is smaller than previous one. Implication for automobiles. Engineers often design coil-over to be slightly underdamped because it provides a balance between comfort and control. The ride feels smooth, yet the vehicle retains stability in a reasonable time. Discussion of damped oscillation graph behavior. The displacement graph shows a slow automatic return to equilibrium. No oscillation occurs, but the system takes a long time to set. Implication for automobiles: overdamping is undesirable because it sacrifices comfort and responsiveness. The suspension feels dead, and the car may not absorb bumps effectively. Discussion critically damped oscillation graph behavior. The displacement graph shows rapid return to equilibrium without overshooting or oscillating. Implication for automobiles: this is theoretically ideal for stability. However, in practice, it can feel stiff because the suspension is motion strongly. It is often used in high performance or luxury vehicles where stability is prioritized.